Okay, so we were discussing scalars, vectors in tensors. And the last time we discussed scalars and vectors, both as examples of quantities that depended on the coordinate system, that transformed in a specific way when your coordinate system changed. So let's just do a little bit more of that and then get on to what we actually want to discuss, which is the Navier-Stokes equation. So let's imagine that we have some vector v in 2 dimensions with components vx and vy. Okay? So if I drew my coordinate system like this, with x in this direction and y in this direction, this vector might be a vector that is pointing somewhere like this. And this would be, the x component would be vx, and the y component would be vy. Instead of writing it as an ordered pair like this, I could also write this as vx times, let us say, ex hat plus vy times ey hat, where ex hat and ey hat are little unit vectors, the point in the x and the y direction. So the way decomposing a vector into components along the different orthogonal directions is a standard test which I assume that you will know. Okay. Now suppose we want to do this in a different coordinate system, and let's imagine that that's also an orthogonal coordinate system, but now you have axes here and here. So this is the new axis x prime, this is y prime, and the components of this vector here are, first of all, this part is v x prime, and the component here is v y prime. Okay? So if I were to start from that coordinate system, I would write the same vector v as v prime, which is vx prime ex prime plus vy prime ey prime. Okay? Because these are now new unit vectors. They point along the axes of your new coordinate system, and all of these components have changed. We require that, since we are representing a quantity with a certain magnitude and a direction, that v and v prime are the same. So v is the same as v prime, although their components in the different coordinate systems vx, vy and vx prime, vy prime have now changed. Okay? So it's obvious that there must be some relationship between the components vx prime, vy prime, and some function here of vx and vy. Okay? So let's just try and ask what is that relationship that we actually have to have. So one way to do this is, let us say, let us write ex prime as some, let's say, O11 ex plus O12 ey. Okay? So I am writing this little vector here as a combination of this vector and a little part of this vector and this vector, which I can always do. Similarly, I can write ey prime as O21 ex hat plus O22 ey hat. Having done that now, let me write down the vector v prime. Okay? So the vector v prime is vx prime ex prime hat plus vy prime ey prime hat. Okay? But now I can substitute for ex prime and ey prime. So this is just vx prime times O11 ex hat plus O12 ey hat plus vy prime times O21 ex hat plus O22 ey hat. Okay? Now let's combine these terms together and write this as vx prime O11 plus vy prime O21 times ex hat plus vx prime O12 plus vy prime O22 times ey hat. Okay? Now this must equal Vx Ex hat plus Vy Ey hat. Therefore, the relationship between Vx and Vy is Vx prime Vy prime must equal, okay, so that sorry, Vx and Vy must equal O11, O21, O12, O22 times Vx, Vy, both with a prime on the right hand side. So this is just writing this particular term out explicitly. Is that okay? So notice that if I wrote this particular matrix of O's as O11, O12, O21, O22, and I call this a matrix O, and I put two lines underneath to denote that it's a matrix, this matrix has a different order of elements. The relationship between this matrix and this matrix is that this is the transpose of that matrix. So this is O transpose acting upon this set Vx prime and Vy prime, which I will just write as O transpose, which is a matrix acting upon the vector V. Okay? So the vector V prime is obtained by some matrix acting upon the entries of vector V. I have changed notation a little bit here, and I am just using the freedom to change things as I want to make it more convenient. I can write this ordered pair of Vx and Vy as a column vector. So we put it in this particular form, and in this way this just becomes a matrix multiplication of matrix with a column vector. So Vx is O11 Vx prime plus O21 Vy prime.
Vx Vy is V, not V prime. I mean,
yeah, sorry. V is O transpose times V prime, exactly. Okay, having said that, since I can also write it in yet another way, which is V index I is just O transpose with indices I, j times V j prime. Isn't that the same thing here? It's just writing out these things component wise. So if I want to ask, so instead of I could put x here. So Vx is Vx prime O11 plus Vy prime O21. That's really what this particular equation writes down. And this is one way of writing it in terms of an actual index rotation. And the other way of writing it is just to say the vector V is the matrix O transpose times the vector V prime. They're all the same ways of writing different things. Sometimes things look nicer and more cute in this representation than if you want to write out the indices explicitly. When I write these with lines underneath, I mean that this is a column vector, this is a matrix, and this is another column vector. Okay. Actually, we have the advantage that we know what the elements of O transpose are, because this represents the new and the old matrix elements in a particular way. Okay, so the vector O transpose is just cos theta minus sin theta, and cos theta. For this particular case, where I have changed this thing here and changed the coordinate system from here to one here that is rotated by an angle of theta. So this is my angle theta here, and this is how my components change. So the relationship between the old and the new components. All right, one thing that I have to ensure is that V dot V is the same as V prime dot V prime. This is because vectors have magnitude and direction. This is saying that the magnitude of the vector is the same. Because V dot V is just Vx squared plus Vy squared, and this must be Vx prime squared plus Vy prime squared. So let's see what we need to. Now that we know how V and V prime transform in between themselves, we can also ask the same question, what must be the features or the properties of this particular matrix in order to make this happen. Okay? So let's use this particular way of writing the equation here. So if V is O transpose times V prime, V dot V, which is basically V transpose times V. So when I say V transpose, I am saying that instead of writing V as an array Vx, Vy, I write it now as a row Vx, Vy. Okay? So V transpose times V is just saying I can use my rules of matrix multiplication by just multiplying this row by this column. So this becomes Vx squared, this becomes Vy squared. This is just Vx squared plus Vy squared, which is a constant quantity. Okay? So V transpose times V is the same as O transpose V prime transpose times O transpose V prime. Okay? Okay, I have it in slightly different notation here, but it doesn't really matter at all. So this particular, if I want to take this object, which is now a vector, and take the transpose, the way I do it is to write this as V prime transpose O transpose. I invert this and now take the transpose of the transpose here. Okay? So I invert these two, take the transpose of both these elements, and then write this as O transpose times V prime, which is just V prime transpose V prime transpose times V here. I'm going to put all of these double things in between, times O transpose transpose is just O. So this becomes O transpose. Okay. Now if this is supposed to be V transpose prime times V prime, then O transpose must equal the identity. Okay. So these are very special matrices, because these are matrices which have the property that if O transpose, if I require that O transpose must equal the identity, then O transpose must equal the inverse of O, because only then can I write O inverse is 1. Okay. So this is a special property of what are called orthogonal matrices. And these orthogonal matrices preserve the norm or the magnitude of any vector that they act upon. Here? Okay, so all I did there was that if I have A, B, which are two matrices, and I take the transpose of that. So what I'm doing really here is saying that this is a matrix whose elements are A, ij times B, jk. So this is some new matrix C, ik. The instruction here is do this multiplication and then take the transpose. So what is the relationship between C, ik and C, ik transpose? Of course, C, ik, the relationship between C and the transpose of C is that the transpose is just the original C. So C transpose, let's say ij, is just C ji. That's how I define the transpose. If you sort of look at what it is, it's just interchanging the rows with the columns. So now if I go back here and say what happens if I take this and ask if I multiply aij, bjk, and then I take the transpose of that, how do I construct this resulting matrix from the matrix elements of A and B? And the answer is that this is B times A. Okay, I interchange these and I take the transpose. So now I can properly multiply this by saying this, the C transpose Ij is just Bi k A k j. So take the transpose, take these elements, multiply them together, and then you get the matrix elements of the transpose. So the important thing is that you have to interchange these two. So you can check that this is all that really has gone into this. The only reason I needed it was to show you that these matrices O must have special properties. But after that, it's not really very important because it's just keeping track of all of these terms as they appear. I could have done all of this by taking care of which index goes where. So just worrying about I and J's and O's and making sure that these matrices are multiplied together properly. Okay. All right, so let's just look at an example of a tensor and see where all of this fits in. So remember that one way we encounter the tensor was to look at the ith component of the force related to the jth component of the normal and say there is a tensor that sits in between here, and there is of course a scalar which is a surface area. So this for me defined the quantity called sigma ij, and I call this a stress tensor. The important thing about the stress tensor is that it connects a vector on the right hand side to a vector on the left hand side. So tensors are linear maps between vectors. They enable you to take vectors and convert them to other vectors here. We know one way of doing this. We can take a vector and multiply it by a scalar. That gives me a vector in the same direction. It's just the length is changed by the magnitude of that scalar. But in general, I might want to do other things to vectors. I might want to relate one set of vectors to another set of vectors. And the object that does that is a stress tensor, is a tensor in general. Okay? So tensors are linear maps from vectors to other vectors. They're special objects. They're not just any set of numbers here. Because if this is a vector and this is a vector, as I change my coordinate system, the components of each of these will change. Okay? But because this is a vector and this is a vector, they have to change in a precise way between coordinate systems, which means that this number here, the sigma ij, must also change. So tensors, like vectors, their components must behave in a particular way as you go from coordinate system to coordinate system. So that's what we want to try and sort of quickly work out, what that relationship must be. Okay. So suppose Fi is sigma ij nj prime, and then Fi prime is some sigma ij prime nj prime. This is in a new coordinate system, just like the change of coordinate system that I did from here to here. This is, both of these are vectors, and therefore these quantities transform in specific ways as I go from one coordinate system to another. So let's just see how that happens, what it does. Okay. So Fi prime, I can say, is taking the Oik times Fk, because I know that I can get the primed quantities by multiplying by an O on the left. So just notice that I have, in order to do that, I have to take the O to this side. So I multiply by the O transpose inverse on both sides. And I use the fact that O inverse is O transpose. So there's a double O transpose here. So O times V is just V prime. And that's all I've used here. That relationship. Is that clear? Clear? Okay. No, I'm just saying that I wrote this in a slightly different. I wrote V is some matrix times V prime. Okay. So now I want to say what is the relationship between V prime and V. So if I multiply from the left on both sides by a matrix that is the inverse of this matrix, then I have only V here. So let's just write it out just in case there's confusion. So look at V equal to O transpose times V prime. Do you agree with this particular result? Okay. So multiply by, from the left, multiply both sides by the same quantity, which is O transpose, take the inverse of that and multiply that by V from the left hand side. This is some matrix. So this is the inverse of the O transpose matrix. And on the right hand side, I have O transpose inverse, I have O transpose here, and then I have V prime here. The matrix times the inverse of the matrix is just the identity. Okay? So V prime is O transpose inverse times V. Okay? But O transpose will be worked out there. As we worked out there, O transpose is itself O inverse. Okay? So I have O inverse, inverse again, equal to acting upon V is V prime. But O inverse inverse is O itself. So V prime is just O times V. So I just said F prime, I want to relate now F prime to F. So I said F prime is just a matrix O times the F. So that's the relationship between this and this. F prime I is O times F. Okay? Similarly, the same thing must hold even the n, if I want to relate n and n prime, I must put a similar O over there. Okay? So, just again sort of relating that back here, I have O ik fk is sigma ij prime, I haven't changed that yet, times O jl times nl times the ds, which doesn't really matter to us. Okay? So I have just made sure this is O jl nl is just nj prime. Okay? And now all I need to do is to take, so I can write this as O matrix times F vector is sigma in matrix form times O times n. Okay? So times the ds, which I don't really want to worry about at this point, is just a number that multiplies each other. So now I know all I need to do is the same trick that I did there. Multiply from the left by O inverse. So O inverse times O times F is just O inverse times sigma times O again times n. Yeah, times the n here, where all of these terms, I have now taken care of what the indices are, times the ds. Okay? So this relationship here has f here, this now becomes a unity operator. This is O inverse sigma O times the n here, and that is just a relationship between f and n, with this quantity sigma ij now defined in terms of this quantity. So sigma prime is just O inverse sigma times O. Was that clear? What do we want to do? What we are setting out to do is, we said that this quantity represents a relationship between two vectors, one on the right, one on the left. So magically there is some operator here that looks at the components of this thing and makes it into something that also behaves like a vector. In order to do that, because both of these must behave like vectors, this quantity must also behave in a certain way in the new coordinate system. It must remember what the transformation is between the old and the new. So now we know how f behaves. We know that f just becomes f prime in the new coordinate system is just O times f. We know that n prime is just O times n. So what happens to this quantity sigma? Well, what happens is that sigma, it becomes O inverse times the old sigma times the new. So now we know what the components of sigma are in the new coordinate system under this transformation. So this is just saying that if you want relationships between vectorial quantities or more complicated quantities that are independent of how you choose your coordinate system, these quantities should transform in particular ways. And this is how the tensor, the simplest tensor, transforms. Okay?
So it's actually sigma equal to O inverse sigma prime.
Did I, yeah, this is correct. No, sigma prime is O inverse sigma O.
No, actually, like, this is the second step. Second step, OF is sigma prime OF.
Is that okay? Yeah.
So you have the sigma prime.
Yeah, that's correct.
So, tensors can be said as linear transformations.
Tensors are quantities that transform in a particular way in these two indices when you go between coordinate systems, and this is how they transform.
So
In general, more complicated tensors will transform in more complicated ways.
which is much more general.
Which is more general, yeah. So I'll give you an example of how they will. So if you work out all of the index algebra here and take into account the fact that sigma O inverse is O transpose and so on and so forth, what you will get is that sigma ij in the new coordinate system is just O ik O jl sigma kl. This is putting all of the information together, sorting out the inverses and so on, making sure where the indices come. Look at how the indices are placed. This is I and j. I is the first entry here, ik, jl, and you sum over the indices k and l. So this says that if I know sigma k, the components of sigma kl in any one coordinate system, I know it in any other coordinate system, because I know all I need is information about how these two coordinate systems are related. And I have already written down the form of O, the form that O takes. So more generally, sigma prime with lots of indices, let us say I, j, k and l, is a set of 4 rows times sigma. So I, j, k, l, let's have other m, n, o, p. So tell me what the indices of the O's should be. So sigma I, j, k, l is
IM,
exactly IM,
then JN,
jn.
KO, and
Okay. So is that clear? Remember that you know the O matrix. We calculated that.
So shouldn't be this like sigma is equal to O inverse sigma prime of right?
Sigma inverse sigma times O. I mean O inverse sigma times O. What's
yeah, it's the same thing. This is also.
Okay, okay.
because O inverse is O transpose.
Okay.
I have to sort of switch those indices together when I write this O transpose here. And writing that transpose is the same as writing the switched index, which is how this works out.
Commuting the two O's like from this.
No, that's fine. That's fine. You're just when you write it in this form, you don't have to worry about. This is just multiplying matrix elements together.
So if multiplying matrix, then the k and j must be.
Hmm? Look upon this just as a way of understanding how to write individual matrix elements out here. So if I want to know what is a sigma prime component xx or xy, I have to sum over this extra index, the k index and the l index, written down in this particular way. And I can generalize this. So it's a good exercise to work from here to how these indices are placed over here. But once you do that, you can see that this is how it will generalize to any more complicated situation. So these tensor objects, sigma, remember that the last time we said sigma of course has in this case 4, 2 into 2 components, but in general 3 into 3 components, because I and j can each take 3 values. And the last time we wrote this as, I think, sigma 1 1 ex plus sigma 1 2 ex ey, etc., etc., etc. And then sigma 2 1 ey ex. And we have to take care of the fact that ex ey ex are not the same, their order matters, and there's not a dot product, it's just a way of writing it out so that we keep track of the fact that this has many different components together. So this, what I did the last time and this notation that I used the last time and this notation here may not be completely sort of, the engineers tend to use this notation a little bit more and they write a lot of textbooks in, so this is called dyadic notation. And this way of writing the two ex, ey, etc., etc. is called a dyad. But this is just finally just notation, and if you're happy with the way I wrote it in component form, that should be enough for you for the moment. Okay, so I want you to remember the fact that tensors are not much more complicated than vectors. They're just objects that behave that you have to put more factors of the transformation matrix, the O's, that connect these two things. But they're required whenever you want to write more complicated relationship between vectors than just simply multiplying a vector by a scalar. Okay? We have figured out various ways of acting on vectors. We multiplied them by scalars, and we can take the dot product with other vectors, which just gives us a number. And then we can take the cross product of two vectors. That's another linear transformation. But the most general way of transforming a vector, one vector into another in a linear manner, is the tensor representation that I told you about. The tensors are what intermediate linearly between vectors and other vectors, and therefore they're very important. For example, as we've been, our earlier examples were regions where you had a little piece of fluid of volume, say ds, of matter volume of surface area ds, and then normal to that. But the force that was acting upon it could be some completely different force, and that force, the components of that force acting upon the surface would depend upon, the components parallel and perpendicular to the surface depend upon the normal to the surface at that point. So this relationship that we wrote down between the force, components of the force and the components of the normal that are intermediated by the sigma ij is one example of the many cases where we will wind up using tensor equations. So you shouldn't be scared about it. Alright, so now what we want to do today and tomorrow is to look at fluids. What we did earlier was to look at solids, and we sort of imagined mass points labeled by P, and these points moved somewhere else, and the displacement between the old and the new point was some u. And then we said, let us consider derivatives of u, so delta u alpha by delta x beta. And looking at the derivatives of u, which tell you how smoothly u changes between different points, we wrote down the forces that were applied. Because we said there must be, if I distort things, then there are forces acting to bring me back. Okay. But this is, remember that a fluid doesn't care about displacements, it only cares about how fast you make those displacements. So this is the original, this you could call this as a strain tensor, but fluids are only worried about the rate of change of this, the rate of change of strain. So that's something that we need to try and incorporate into our description. The way to think about fluids is first to think about what are the conservation laws that apply to the fluid. Okay, so I have a piece of fluid here. I have mass points inside that fluid. I might want to look at regions that are somewhat larger, that don't contain just one particle or two particles, but maybe something like 10 to the 10 particles at a time. And they all, because fluids are cohesive, these particles inside are more or less doing the same thing. Okay, so importantly, what I want to think about are the densities, the mass densities, rho, point x and t, as well as the momentum density, say g at point x and t. These are ways in which I characterize the fluid. I can also say how much energy is there. So if I tell you, look at point x and time t in a little neighborhood, E of x and t tells me the energy density inside that region. I can choose more complicated things. But these are important because of all of the ways that I could use to describe what the fluid is doing here. These quantities are conserved quantities. Remember what we meant by conservation laws. Remember this old equation that we wrote down where we said, suppose the density at any point is given by rho of x and t. If the density is conserved, what that really means is the density can only change when particles leave the surface or enter the surface. So that's the only way density could change. And that meant that if I asked, how does the density change at a point x at time t? So this is the rate of change of density at point x at time t. This could only change because stuff left at the surface. Therefore, I could write it in the form of minus del dot j. This is the most important equation that we wrote down earlier. We called it a continuity equation. And we spent some time discussing its properties, where j is a current. So j is the density rho times the velocity v. Okay. And all this was saying is that in a given amount of time, we have to just count the number that are leaving the surface. So this is just an integral of the current over the surface. But then this can be made to a del dot j over the surface. This amount equals the rate at which you lose mass from the surface. But now I can just say, look at a specific volume and say this must equal this. And this is a negative because particles, I will count particles leaving as a decrease in the density, which gives me this particular equation. That's how we came about it, the logic that we employed. And the sort of justification for doing all of this is that we want to look at local densities. So at every point we want to think of velocity fields, currents, energies, densities, etc., etc. And then we can write down these partial differential equations that describe them. Do you remember this? I hope everybody remembers this. But we even pushed it a little further. Remember we said for a diffusing particle, the current J is in its simplest form d times the gradient of the density. So there is no current if the density is constant. If there is a gradient, then there is a current, and the current flows from higher density to lower density. And the minus sign accounts for that because normally the gradient of rho, this is a vector that points from lower to higher. So I put a minus sign here, that's a vector that points from higher to lower, and d tells me how fast they move, roughly speaking. So if I put that back in there, I have delta rho by delta t is minus del dot j, which is minus del dot minus d times del dot grad rho, which is d. So minus, and there's a minus here, minus and minus gives me plus. So this is d times del squared of rho. And this equation here is your old diffusion equation. This is the logic that we have been pursuing to understand that. But now we need to worry about a new equation. So we have, this is something that we understand well, how we use the continuity equation just to describe the conservation of particle number. But fluids have other conservation laws. And the other important thing that is conserved is the momentum. Okay? Remember that in physics, there are three, if in the absence of forces, torques, etc., anything that changes the energy of the system, momentum is conserved, energy is conserved, and particle number is of course conserved as we showed here. So how do we write down the effects of momentum conservation? The Navier-Stokes equation for a fluid is the way that expresses the fact that momentum is conserved over very short length scales. What do I mean by momentum is conserved? That means that if I want to create an acceleration, if I want to change the momentum, I must apply a force. So what we want to do is to apply F equal to m times the acceleration here, or in general F equal to rate of change of momentum here, to a little piece of fluid inside here. So I want to ask, what is the rate of change of momentum term that applies here, and what are the forces that are acting on the fluid? If I know the forces that are acting on the fluid, and I can equate that to the rate of change of the momentum of the fluid, then I have the equation of motion that this little piece of fluid actually obeys. Okay? All right. So now, so let's now ask, what is the rate at which momentum changes or decreases, let's say, inside the fluid? And that is minus, if it's decreasing, d by dt times the integral of the mass density times the velocity into the little volume. I'm going to consider a fixed volume of fluid over here and ask, how is momentum changing? The answer is, this is the momentum inside the piece of fluid. It's a mass times the velocity, which is p. Remember that p is mass times velocity. Okay? So this is the mass density. So I'm looking at each little point. The velocity at that point integrated over the little volume that I'm considering. All right? And then I can just take this inside and write this as integral over v delta by delta t of rho v times dv. I'm just taking this particular thing inside because the volume is fixed and its shape is fixed. So there's no additional term, it's just this d by dt acting upon this object here. Okay, so where do the forces come from? Where does forces and momentum flux? So this particular term here is this side of the equation, the rate of change of momentum here. But now we must also worry about momentum convection. We must worry about surface forces, and we must worry about body forces. So let's look at the first part of it. So here is my surface here. Now the velocity field will move stuff through a little surface element, ds. It's moving momentum just by the fact that things are moving with the velocity locally. So this is rho times v, okay, times n hat dot v times ds. Okay? So this is momentum in the direction of the normal, because anything perpendicular to the normal doesn't add to the fluid inside here. Okay? So this is momentum coming into the fluid here, momentum here into the fluid, little element of surface. Okay? So this I can write as n hat dot rho v v. And now this object here is actually a tensor.
So what is n cap dot v?
This is the component of the velocity field in the direction of the normal. Okay. So we have a surface here. Let us say we're looking outside here, either outside or inside. This is the normal. We want to ask how much of momentum is coming in per unit time through that. So that is this is the amount of momentum coming in per unit time. This is that fraction, that component that is in the direction of the normal, and multiplying it by this little surface element is telling me that this accounts for everything that is coming through that surface. Okay?
If it was going to outside, we will say B dot n cap, right?
So we have to worry about the signs that we're doing. No, this is the component along the normal, but n hat minus n hat dot v is the component is what is left over from that. Okay, so it's actually v minus n hat dot v times n hat. So look at what this means. This says look at the component of v in the direction of the normal and multiply it by the unit vector in that direction. So this actually the stuff that is coming in like this. There's all the stuff, the remaining part of the velocity field is stuff that is going along this direction. So that is the total velocity field minus the part that is going in that direction. So v minus n dot v n hat is the stuff that is perpendicular, which we don't worry about at all, because all we are worried about is how momentum is reaching this little chunk here from the outside. Now we can do our trick of taking, instead of integrating over the whole surface, we can write it as a del dot something. Okay, so remember this is along a bit of surface, how much momentum is coming in through convection here. If I integrate over the surface, that is the total momentum coming in through convection per unit time. But now I can convert this into a del dot something over a volume. So that then becomes an integral over the little volume del dot rho v v. So that's one part that we've actually managed to write down. The second part, which is the surface forces, remember we worked out the surface forces. The first surface forces are given by F equal to sigma times n. So Fi is sigma ij times nj times ds. Okay. If I integrate over all of these forces, over the full surface here, that tells me the net force that is acting through the surface on this little volume. But again, I can do the same trick of making that a del dot something. So this then becomes an integral over the little volume del dot sigma. Okay. The only slightly tricky thing here is that I have to be careful about where these forces, the sign of the forces from the outside. We can say that forces acting into the surface, acting on the surface here. So this is inside and this is outside. The forces acting from outside to inside will be counted with a negative sign. So it's often normal to put a minus sign here and associate a minus sign with this, because this tells me what is the direction of the force. And that is something I must say from outside. Given there's an outside and inside, I can choose this force, the component to be either directed into the normal or against it. So we will take the point of view that all forces, the signs of all forces that point inside from the outside will be negative. So we can discuss all of them. Huh? Here you don't have a negative because you're just counting the flux that is inside. You don't need the negative here, but there you need it. Because this is a choice of, in a sense, a sign of the sigma. We'll put things together and then we'll sort of justify each one of these separately. Okay. Of course, the last part is, of course, the bulk part, which is an integral dv times rho times whatever, say, the g, if this comes from gravity. So let's put everything together. And the way we will do it is to say, first of all, the term that comes from here, which is delta by delta t of rho times v. That's one term. So this is the rate of change of momentum on the left hand side. That is the dp by dt term that I have here, equal to ways in which the momentum can change. So one way is through convection. That is a term that we accounted for here. So that is minus del dot rho v V. Then there is a contribution from these terms here, which is minus del dot sigma. And then there is a third term, which is the force term, which is rho times G. Okay. Actually, you might be right about the sign here, because I think the sign should be negative, because this is the del dot J. So the stuff that is coming in must have that negative sign, which is why this term is written out here. The minus sign comes from here. You're right about that. So this is now our equation of motion, where we've taken different parts of it. This is change of momentum inside this little volume by convection. This is surface forces as given by a stress tensor. And this is body forces as given by the force of gravity here, G. But in general, could be anything else. So this is an equation that we would write. Sigma is a tensor. So when I say, again, I didn't explain this the last time, but let me just explain it now. That given, let us suppose I have some vector A with components AI. And let this vector depend upon space. So A depends upon the spatial quantity x. It could maybe even depend upon the time t. The derivative of the vector, which suppose I write down as delta I Aj, is itself a tensor. What does that mean? A is a function of x, y, and z. So A is Ax as a function of x, y, z, and t pointing in the x direction, plus Ay as a function of x, y, and z, and t pointing in the y direction, and Az x, y, z, t pointing in the z direction. Okay? So the components Ax, Ay, and Az depend in a complicated way on x, y, and z. So if I want to take a derivative, let us say, let me take a derivative of any one of these components. So let us say the x component. So let me write Ax, which is this term here. In general, because this depends upon x, y, and z, I can take the derivative with respect to x, I can take the derivative with respect to y, I can take the derivative with respect to z. Okay? So the quantity delta I Aj says take the derivative with respect to index I, which could be y, let us say, of the component which could be x, y, or z, whatever it is. So this is just one example where I look at, say, delta x, Ax, delta x, delta y, Ax, delta x, Ay, etc. There are 9 such combinations that we could make. This is also a tensor. That is to say, this combined quantity with 2 indices also behaves exactly as we showed earlier. It behaves with 2 factors of O. When you ask how does it behave when you go from coordinate system to coordinate system. So I didn't stress this the last time, but this is something to remember, that the gradients or derivatives of vectors are higher order objects called tensors. So this is a way of promoting a vector by taking a derivative to something with 2 indices and not just 1 index. So delta I Aj might be some vector, let me call it phi I, some tensor called phi Ij, which behaves completely like a tensor. Okay?
So the normal gradient is not
The normal gradient gives you a scalar. So the normal gradient is taking delta I Aj and multiplying it by a further delta Ij. When I do that, I set j equal to I. This becomes delta I Ai, which becomes del dot A. So now I have a scalar instead of what I had earlier. I have a number at every point x, y, z, and t.
del
is a divergence. Yeah. The divergence of a vector is a scalar. So now from this vector by just what I said is contracting over these indices, which is the same as multiplying by delta ij, I now have that scalar. But this is a specific case of a more general quantity, the delta I aj,
So
which is a
this
tensor.
only because the components of a vector like ax is a function of x, y, z, and t, right? If ax was just dependent on x and ay just on y,
Then lots of these components will vanish. But in general, that's not true. In general, the x component of the field will depend upon x, y, and z, wherever it is. Just take as an example, just take example of any field that is, say, radially symmetric here. That it has some value that depends upon how far it is from the origin. So if I write this in x, y, and z coordinates, each component here will depend upon what are the x and the y and the z that I have. So the x component ax will depend upon x, y, and z. The y component ay will depend on x, y, and z, and so on. So this is by far the more general case. No one said that this x component should depend only upon x. It could depend upon whatever it is, x, y, and z. Okay. There's one bit of simplification here, and that comes from the fact that we have another equation, the continuity equation, which is delta rho by delta t is minus del dot rho times v. Okay. If I operate del dot rho times v here, one of those terms will cancel with one of these terms here because of this particular relationship. So rather than do that algebra, I'll just leave it to you and write out the final equation. The final equation is rho times delta by delta t plus v dot grad acting upon v itself is minus grad. Okay, so let me write vi. So minus grad j sigma I j plus rho times g. Okay. So that term here, the del dot sigma is written as grad j sigma ij. So now I want to write everything in terms of each individual component here. So instead of having this vector relationship here, I will now write each particular term out specifically. What I will get is rho times delta by delta plus v dot grad acting upon v. V dot grad is just vx delta by delta x plus vy delta by delta y plus vz delta by delta z. Okay, that's what v dot grad means. That v dot grad acting upon v is the term that comes from the stress tensor and the term that comes from any body force on the right hand side. Okay.
So v dot grad is an operator.
V dot grad is an operator, exactly, because it operates on anything that is on the right hand side. And in this particular case, it operates on the vector field, on the ith component of the vector field. So you can, so suppose I want to ask how I just need to put in vx, vy, vz over here and solve this particular thing. The only thing that I have not told you is what is sigma ij and how do we calculate it in terms of the properties of the liquid. So sigma ij right now is just the forces that are exerted on a particular surface from the outside. But those forces must depend upon what the liquid is, what its properties are, for example, what the magnitude of those forces are set by various other complicated things. So now the problem reduces to asking what is sigma ij, what is the form that the stress tensor of the liquid takes. Okay. Is that clear? So this final equation, you just write it out here. We can look at it for a while. delta by delta t plus v dot grad acting upon v is minus v ith component is minus grad j sigma ij plus g times the term that I wrote down. Yeah. In fact, in general, I will just drop this term altogether because I will assume that there is no body force. I don't want to worry about an additional body force this time. This is an equation that is called the Navier-Stokes equation. Okay. Notice that I have not written out the form of sigma ij. When we do that later again, maybe I'll spend a little time justifying it. The equation that I will get is rho times delta by delta t plus v dot grad acting upon vi is, okay, acting upon v is eta times del square of v minus gradient of p.
So how did we get
This term here, we just put every little piece together. We said the term on the left was this particular term. This term is a derivative of rho with respect to t, derivative with v with respect to t. Then we simplified this. The del acts on three different parts. There's a grad rho term, there's a grad v with the rho and the v outside, and there's another v here. So we took some part of that and some part of this particular term and combined it and got rid of that by using this particular equation. I skipped some steps there, but I didn't want to get bogged down in algebra. So I'd like you to do that. What's left is this particular term, the minus del dot sigma term. And then there is a body force which we can then get rid of. That simplification enables me to write things in this particular form. The rho delta by delta t times vi, and this term comes from the fact that v is itself moving. So this is called the kinematic term. And this is a term that makes this equation very difficult to solve because there's a v here and a v here. So this equation becomes non-linear. Because this equation is non-linear, it's therefore a complicated mathematical problem to solve. But all this equation says is just force equal to m times acceleration. It's just written out in a complicated way, in this particular, sort of in a seemingly complicated way.
It's basically the movement, like the force that is applied on a fluid.
That's right. So all the terms on the right come from the forces that are applied on the fluid. This term comes from the fluid itself moving. And so it's convecting itself from point to point. That term comes from here, which is convective term, that is the nonlinear term here. This term comes from the forces acting on that little piece of fluid, and this comes from the body forces. These are surface forces, these are body forces. So what we need now, as I said, is to find a relationship between sigma and the velocity or the gradient of the velocity, etc., etc., etc. It turns out that once you do that, which we can do the next time, it turns out that the liquid is defined by a pressure and by what is called a viscosity. So both these terms actually are lurking in the definition of sigma. If we choose sigma correctly, and that is what, this is for a fluid called a Newtonian fluid, which is a relationship between sigma and the velocity field. If we do that, then the final set of equations is a set of equations that looks like this. And this is really what is called the Navier-Stokes equation, although this is a slightly more general way, which emphasizes the role of the stress tensor on the right hand side. So where this may look like a lot of mathematics, but remember that fluids are everywhere. When you talk about if you talk about bacterial swimming, bacteria must swim inside fluids. And so what the fluid does is of great interest to the bacterium. And what are the strategies that a bacteria might employ in order to move must be reflected in the properties of the fluid and how the bacteria is able to transfer momentum to the fluid. Anything that you might consider in the cell, virtually anything happens in a liquid environment. Transcription happens in a liquid environment. Any type of polymerization happens in an environment that is liquid or fluid in some form. So we have to understand in biophysical terms what are the effects of including the properties of that liquid, of that fluid. And the simplest way of thinking about fluids, or in fact the only way we know currently of thinking about fluids, is in terms of equations like this, the Navier-Stokes equation. it turns out that in biological systems, there are many interesting approximations that you can make. For example, in many cases, you can get rid of this term completely, altogether. And then all the bad business that the nonlinearity brings, you can just get rid of. The whole problem becomes a linear problem. That's called the Stokes limit of the Navier-Stokes equation. And in that limit, very interesting things happen. And it turns out that bacteria are in precisely that limit, where I can neglect this term here. So the strategies that bacteria use to swim are very different from the strategies that we use to swim. We transfer momentum to the fluid by essentially using the inertia of the fluid to push ourselves forward. But here we have neglected inertia completely. It's completely out of the picture for a bacterium. So the bacterium must use a different strategy, which is not dependent on inertia, in order to move. And the way the bacterium like E. coli do it is to take flagella, bind them into a helix, and then rotate the helix. I must have mentioned this earlier in some earlier context. But that really comes from the fact that the bacterium is swimming in a fluid, it is having to interact with that fluid, and we must ask, how does the fluid respond to forces that the bacterium exerts? If we know that, all of that goes into the stress tensor, the boundary conditions on the flow. Okay. Then from there we can figure out what is the velocity that this motion induces in the fluid. Is that enough to propel the bacterium forward? So it's this interaction between things that move in the fluid that is very important to doing any sort of biophysical calculation, the biophysical estimation of what might be important constraints on the very functioning of biological machines. They must function in an aqueous environment. Okay.